Right. In the last session, we discussed the design of phase need compensators so that we can get the controller or the closed loop system to give us the right crossover frequency and the right phase margins so that system becomes more stable. That's really the aim of using phase need compensators. Now, to the opposite to the phase need compensator, we have something also called phase nag compensators. Now, phase nag compensators are used entirely different, in a different way to phase need. Although the transfer function looks very similar. Well, if you look at equation 1, that looks like exactly the same as phase need compensator. But in there, we have alpha value that's less than 1. So alpha is greater than 1 will give you the phase need compensator, that give you the positive phase angle. Alpha less than 1 will give you a phase angle in the negative region. And if alpha value is smaller than 1. Now the way to calculate alpha and beta and tau value is similar as well, except in equation 2, in the phase need, it's 1 plus sign over 1 minus sign. Now for the phase nag, is 1 minus sign over 1 plus sign. The equation for calculating tau value is exactly the same. Okay, so if you know the maximum phase angle you can allow, and also you want where the frequency for the maximum negative phase angle to be, then working out the alpha and tau value is straightforward. In this example, and if I say I want to have a phase nag compensator to give me a maximum phase nag of 45 degrees, that's negative phase angle of 45 degrees, at omega at a frequency of 10 radians per second. I just apply the two equations. Alpha equals to 1 minus sine 45 over 1 plus sine 45. That will give you a value of 0.172. Of course, that's less than 1. It just confirms what I said earlier. To work out the tau value, you apply the second equation, where you use alpha value from the first calculation. This is the frequency where you want the negative phase angle to be. So that will give you alpha tau value of 0.2414. So that calculation itself is quite straightforward, but it is the application of phase nag. We use it for entirely different scenario or different purpose. Okay, so the 4 steps I introduced or I explained in the design of phase need compensators don't really apply here. So don't try the same approach as you use for designing the phase need. Now, phase nag compensators are typically used to increase the gain or the magnitude at certain frequencies or at a lower frequency, if you say so. Now, if you look at this diagram here for this particular example, you can see the magnitude varies with frequency. Okay, so at lower frequency it's higher, at higher frequency it's lower. So it's really trying to use this to increase the lower frequency gain. And typically, we will try to move the frequency at which you get your maximum negative angle somewhere away from the crossover frequency you design for closed loop system. So it doesn't affect the crossover frequency much, because we don't want to add a negative frequency anywhere near the crossover, which will reduce the phase margin, which is no good. Okay, so what would normally happen for a phase nag is we replace that small k in front of this fraction with 1 over alpha. So we actually, if we know how much gain we want, we just say, right, I can work out alpha value to give us a gain as required, and then we move the frequency to a much lower value. Okay, so in this case, we would work out alpha value first, because alpha is smaller than 1, then 1 over alpha would be greater than 1. Greater than 1 will give me a higher gain at lower frequency. You see in this plot, it shows a gain of 15 dB, which is more than 0 dB. 0 dB will give you a gain of 1. Okay, so 15 dB will give me some positive angles. Positive gains that help to reduce the steady state error, as I will explain in a minute. I will give you an example here. Say design a phase lag compensator to give a DC gain of 5 and the frequency of a negative maximum phase angle at omega m equals to 1 radians per second, and also find the negative maximum phase angle. So we no longer want to work out the phase angle first, because this time we get negative phase angle, which is not really what we're designing phase lag for. Okay, we are here to try to increase the gain. So the first step is actually try to say, right, if I want a DC gain of 5, then of course, if I defined the k equals to 1 over alpha, now if you look at that transfer function, equate s to 0, equate this s to 0, it will give me a DC gain of 1 over alpha. DC gain 1 over alpha, but I want that to be 5. Therefore, alpha will have to be 0.2. Now from 0.2, that's the first parameter you calculate, and I can work out the tau value because I know where I want to put that negative phase angle, or what frequency I want to put that negative phase to be, which is 1 as in my requirement. I want omega m equals to 1. So I replace this alpha by 0.2. I replace that omega m by 1. That will give me 1 over 1 times square root 0.2, which will give me a tau value of 0.25. And I can actually find out the phase angle as well, because this equation, if I just go back there, this equation here, okay? Because in my first calculation, I work out the alpha value. This will give me a maximum phase angle of 41.8. It's actually a negative value, okay? It's a negative phase angle. But the equation will give you a positive value. But you should know this is actually a negative when you substitute everything back into your transfer function. Because we work on alpha and we work on tau, therefore we can substitute everything into the equation. So this will be 1 over alpha should be 5. I'm sorry about that. This should be 5. 1 over alpha should give me 5. And then the rest is follows. Okay, all alpha there, tau there, and tau there. Okay, and that's how you use the phase lag compensators to give you a higher gain at low frequencies. So really, what we've done here is to say, right, we have a phase need compensator that will give us a positive phase, help to improve stability, help to give us more phase margin, and help us to define where the crossover frequency should be for the closed loop. Well, for the phase lag compensator, what we're trying to do here is to increase low frequency gain, in particular the DC gain. Therefore, the steady state error will be reduced. Now, if you think about the phase need, to give us more stability. Think about phase lag to give us more low frequency gain or DC gain to reduce the steady state error. We can compare that with what we've done before, the PID control. Okay, so we actually compare that with PID control. We said that before. The D term in the PID control helps to improve the stability. The integral gain, the I term, helps to remove the steady state error. So there are some similarities there. Okay, so in fact, the phase need compensator is very similar to the PD controller, proportional and derivative control. The phase lag compensator is very similar to the PI control. It's just that they don't go as extreme as PI or PD. I can do some comparisons here. Okay, this is a transfer function for the phase need compensator. This is the transfer function for the PD controller. So you can see some commonalities here in the numerator. In the numerator, there's a 1, there's some value times s, then there's a k. Okay, this is also in the numerator, there's some value there, there's some value in the numerator. It's just the denominator that you don't have for PG control. And for the phase need compensator, we actually can define the positive phase angle at specific frequency. That's where we calculate our tau value. The lower frequency gain is k, so if you equate this s to 0, this s to 0, the DC gain is k. But the high frequency, you will have a higher gain because if s tends to a very large value, then the first term will be much greater than 1. Therefore, you can neglect that 1. The tau value will if s is very large in the denominator, then tau times s is much greater than 1, so you can actually neglect that 1 as well. Alpha tau divided by tau s, that will be alpha. So in the high frequency region, the gain for the phase need compensator will be alpha times k, but it is finite. Okay, but also we know that it is easy for us to move the crossover frequency to be where we want them to be. In contrast, PD controller will also give you a positive phase angle, but it's less defined because PD, when you get to a very high frequency, this is j omega, therefore, when frequency tends to infinite, you get a positive 90 degrees. It's harder to control. It can be a higher phase angle, but it's harder to control where you want it to be. The DC gain at lower frequency is proportional. For s equals to 0, then this is the GP. At higher frequency, the gain will be very high because this second term, s equals j omega. And that, if omega tends to infinite, then the second term tends to infinite. Okay. So we have to be a little bit careful because sometimes we have problems with noises. Noises often happens at high frequencies. So if your gain or the AC gain at high frequency is high, it tends to amplify the noises. And that's really one of the drawbacks for using PD controller. And often you have problem with noises. Okay? Of course, phase need has its own limitations because it doesn't give you as much the positive phase angle as you might get from PD control. And the design process is probably a little bit more complex. But in essence, their aim is the same, which is to increase the stability and phase margins. Now, let me just look. Phase lag compensator, however, can be compared with the PI control. Phase lag will give you a higher lower frequency gain or DC gain of 1 over alpha, which is greater than 1. At high frequencies, it will be 1. So it doesn't really affect the frequency at high frequency. So it doesn't affect the gain at high frequency. The PI control, on the other hand, it has an effect of removing the steady state error, because at lower frequency or at 0, something 1 over or something over 0 is infinite. So the lower frequency gain will be infinite. Therefore, the DC gain is infinite. Open loop DC gain of infinite will help to remove the steady state error when your input is a unit step. But also it introduces a negative 90 degrees at lower frequency, which is a little bit worrying because you don't have much control over how much angles you get. Negative phase angle adding into an open loop transfer function tend to have problems for stability. That's why when we use PI control, we have to be careful with the gain. Too much of an item will cause instability. At high frequency, and we don't need to worry too much about it, because 1 over S tends to 0, so you only have a GP to deal with. Okay, so the main difference is here is that phase lag will give you a high gain at low frequency, but not quite to infinite, like PI control. It helps to reduce the steady state error, but it doesn't remove it altogether. And that's the main difference here. The worry for the item alone, the PI control, or something you need to be careful with, is that the item tends to cause instability. So the gain has to be fairly moderate. Okay, so I have another practice, or a couple of practice questions for you, and just for design of phase lag compensators. Okay, question 1, I give you the frequency, and I give you the phase angle. I want you to work on alpha and tau value. Second one, I want a DC gain of 5. Therefore, I want you to design alpha value for me, but I also want omega m equals to 1. Hang on, is that the same as my example? It's probably exactly the same. Now I'm going to change that question, okay? And also go back to my PowerPoint for the question 2, not this video. If you go back to my point, I will have changed the set question number 2 for you. Okay, so you can have a different example to practice the design of phase lag compensators. I just, for some reason, I use the same values for the question as to my examples, which should not happen, but I'll change that. Thank you.